Hey, have you ever wondered what would happen when the stars eventually explode in this big universe? That is what computational astrophysics is always exploring. So in this video, I'll explain, as a computational astrophysicist, how I explore the effects of stellar rotation on stellar evolution. I hope this video can guide you to experience how computational astrophysicists travel through the universe and look at the stars. Cell evolution means the process from the moment the stars were born to when the stars die. Stars initially are molecular clouds, then stars with 10 or more solar mass can form heavy elements. As the stars form the iron cores and the iron core fall velocity reaches 10 to 8 kilometers per second, we will define them as turning into the pre-supernova stage, which means the stars would have the possibility to become supernovas or black holes. So, later in this video, we shall explore whether rotation makes the stars more easily step into this pre-supernova stage. For computational astrophysics, the true mystery does not lie in the telescope, but among lines of codes and physics formulas. The massive universe becomes a tiny part of the computer screen. Intuitively thinking, whether the star rotates or not shapes how chemical elements within the stars interact with one another. Nevertheless, most simulation models are not set up with the effects of rotation due to technical challenges and the intention of simplifying parameters. Hence, I constructed one-dimensional models for massive stars of 20 to 40 solar mass, considering different rotational rates from omega equal to 0.1 to 0.9. The result of my model suggests that the rotation leads to a better convective mixing. The figures here show the chemical abundance of a rotational and non-rotational star. The x-axis means the star radius, 0 represents the deepest inside of the star. The y-axis means the amount of chemical elements, and the lines with different colors represent different chemical elements. We can observe that rotational stars at the right-hand side shows the better chemical homogeneity, which means the chemical elements inside the stars are mixed more sufficiently and could contribute to the formation of the iron core. Run the model to the end, we will see that the rotational stars represented by the blue dots compared to the non-rotational ones represented by the red dots form the iron core that reach the velocity to become pre-supernova more easily. That is to say, the stellar rotation drives the stars to enter the pre-supernova stage more easily. So here's a small computational astrophysics attempt to know the universe slightly better. Hope you enjoy it.